Hello, everyone, and welcome to today's webinar, Advanced Backend Automation Technology. And before we get started, I'd like to go over a few items so that you know how to participate in this event. You've joined the presentation listening through your computer speaker system by default. If you prefer to join audio over the phone, just look for the audio section of the GoToWebinar control panel and select phone call, and then the dial-in information will be displayed. You have the opportunity to submit any questions you have to our presenters today. Just type those questions into the questions section of the control panel. You can send those questions in at any time. We are collecting them and we'll address them during the Q&A portion at the end. Today's webinar is being recorded and you will receive a follow-up email within 24 to 48 hours with a link to view the recording. And I would now like to introduce Alan Weber.
Yes, good morning, afternoon, or evening, depending on where you are. In fact, it could be middle of the night if you're one of our Asian colleagues. We are very glad you're here. This is an exciting topic for Brian and me because we've been working in this domain for a good while and have, I think, interesting technology and activities to share with you today. So again, we appreciate your participation. We hope you will find this is one of the best spent hours of your week before it's all done. Okay, let's skip forward. All right, here we go. Okay, so here we go. What we'll cover is a little bit of background and motivation for this particular topic, talk about a solution approach and the major innovations that are part of that, give you an idea of the current status of that development, and finish with conclusions and next steps. So just to get a kind of a baseline level set here, since we're talking about automation in the back-end facilities, the question is, what percentage of the back-end equipment have some kind of standard data collection interface, whether it's SexGEM or OPC-UA or some other standard. So this will give us an idea of what our baseline is among the participants. So we've got, I think we'll run this for 25, 30 seconds and see what comes back here, see where we are. Okay, over 75%, 21%, 17, 25. Okay, well that confirms, I think, what most of us believe the status of the backend is, and that gives us an idea of what the opportunity is in this area. Those of us that have also spent a great deal of time in the front end take this kind of thing for granted, and you can't do that in the back end for a variety of reasons that I'll cover here in a minute. So I think that means we got a great audience for this topic. So, okay. So the automation challenges in the back end, and again, in contrast to the wafer fabrication facilities, are listed here, some of the high order ones. First and foremost, of course, is you have multiple material transformations. You know, in the front end, you've got a wafer that goes in, a bare wafer, and comes out the other end, a patterned wafer. Not so in the back end. You've got at least 3 transformations, and depending on the complexity of the product form factor, you may have more than that. So that adds a level of complexity. It's also more of a linear flow shop rather than a cyclical environment. That actually makes some things easier, but it does make things different. There's, of course, a high product variety and velocity compared to the front end. So things happen more quickly and with more units, which is, of course, creates a bookkeeping issue. There's also, because of the level of automation and the interfaces you saw, significant manual intervention, either from changing setup or messing with fixtures or entering manual recipe codes or failure codes, a lot of stuff that happens in a back end that you don't see in the front end, which is a source of either error or delay or both. Of course, on the back end, the unit product traceability is more complicated because of the material transformations and because there's so many more of them. In the front end, you really have to just know where a wafer goes from its input FOUP slot to its output. And if you can track that, then you're pretty well guaranteed knowing what happened to every wafer. Again, not so in the back end. From a cost standpoint, relative to front-end equipment, you have a lower unit equipment cost and budget, which is, but that doesn't mean the problem is any simpler. And so this is a challenge. Of course, the semi-standards have been leveraged in both environments, but they're pretty much ubiquitous in the front end, whereas in the back end, you saw the stats that we had just a minute ago. So, and then finally, because of that less adoption of some of the standards, you'll have multiple data source types and protocols to manage, which again adds to the challenges. So no shortage of things to address in this environment. And again, this is part of what we'll be talking about today. All right, I talked about material transformations. Of course, the output of the front end is the input to the back end. So you've got a patterned wafer that goes mounted onto a frame that is then sawn into individual devices on that Mylar frame and then picked off and put into a strip or a lead frame. And then a number of processes deal with that lead frame. And then finally, those are separated out, cut and formed into individual packages. And so there's at least 3 material transformations that go on from a incoming wafer to a the final chip. All right, of course, there's the sort of automation topics that are generated by this list of challenges and materials are handling multiple carrier types. So you'll start with a FOUP or a front opening unified pod in the case of a 300 millimeter factory, and that'll be separated after the devices are put into to lead frames into magazines, which may be layered into trays and carts. You also have the challenge of nested carriers, or you have carriers of carriers that are moving around a lot of times manually that have to be tracked. And Brian will talk more about the specific carrier types that we've dealt with here. Of course, augmenting equipment data with human input is a challenge. Many times, if you're trying to do an accurate OEE assessment of equipment, you need an operator to tell you why something has gone into standby or gone into waiting for maintenance of some type. So the human is at this point still involved in that data collection loop. Of course, managing WIP buffers, if a person never touches something and you only have material handling systems, you can keep track of that in the front end. In the back end, you may end up with a WIP buffer, which is just a zoned out area on the floor, or a corral, as some companies have called it. And you have to know where to go get the material that's to be moved to the next stage. Consumables and durable handling is becoming a new challenge because of the importance of the lot information from those components that go into the traceability equation. So that's becoming something to deal with. Of course, integration of simple equipment, just because it's simple doesn't mean there isn't useful data that needs to be collected from that and incorporated into the analysis system. So the equipment that may have had little or no connectivity to a factory system needs that going forward. And of course, compliance testing for non-standard requirements. To run an automated factory, you have to know that every piece of equipment is a good citizen of that environment, and that usually requires some kind of acceptance testing of those interfaces, which can be tricky for non-standard requirements. And then finally, getting this message out to the supplier base, both of suppliers of equipment, materials, carriers, software. It's a whole new world for this. So. All right, so here's the poll question number 2 for those that are again familiar with the different types of equipment. I've got a spelling error on die bond. That should be DIE. We're bonding die, not hair dye or clothes dye. But yeah, pick among these things which ones present the most challenge from a automation standpoint and therefore data collection requirements. And we'll give you 20, 25 seconds to select those. Okay, let's see. Wirebond final test. Oh, that's an interesting number. Wirebond typically bubbles to the top of careabouts because of the some of the importance to the reliability of those bonds. But it looks like that's pretty evenly spread. Of course, final test is a big deal because that tells you, how well the chips perform. So, all right. Well, thank you. That's great. That's great input to have as well. All right. So moving forward, let's talk about a solution to this family of challenges here and the innovations that are part of that. And again, here we have leveraged heavily the insight and effort of Infineon Technologies. They're a longtime customer and partner and technical colleague in this area. And what they have done is adopted an idea that was put forth in the mid-90s when the 300 millimeter transition happened. And that's to actually define operational scenarios that govern the communications among the various system elements that are in an automated system. And so rather than just listing, hey, please support the GEM 300 messages, they go beyond that set of requirements and say, let's actually go through a sequence of events and a sequence of message interactions between the components of the system, pardon me, that makes it clear exactly which messages are necessary to achieve this level of full automation. They've called, Infineon have called this their target equipment integration sequence, and it is explicitly referenced in the latest tool operation specification, also called the TOS, for the back end. People that have supplied equipment and systems to Infineon know the TOS very well. It is a very explicit set of requirements, and in the most recent update, the back-end TOS has this target equipment integration sequence in there. It shows the specific interactions among the elements of the system according to the list of GEM 300 standards there. So the E39 object services, dealing with control jobs and process jobs for E40 and E94, handling carriers, not just of FOUPs or cassettes, but all the varieties of carriers that you have in the back end, some of which I mentioned a few minutes ago. Substrate processing and tracking, and again, a substrate here is not necessarily just a wafer or a single device. You'll see in Brian's slides, what the range of substrates is that has to be handled. And then finally, a new topic for which there is not yet a semi-standard, but which we're working on, is a standard to actually track consumables and durables. So all of these items are explicitly referenced in the TOS backend, and this level of specificity enables you to actually validate the implementation by standard GEM protocol test software. So that's the benefit of having an operational scenario done at this level. So what does this actually look like? Well, the target equipment integration sequence is, for those familiar to ladder diagrams for system communications, it's a ladder diagram with 4 communication partners. At the very, pardon me, the very left rung of this ladder is the operator, robot, or AGV, which is responsible for loading material and you may be hitting a start button and occasionally providing input. The next layer, of course, is the equipment. This is where the processing happens, and this is where most of the communications happens between other elements of the system. So this is where the equipment suppliers need to look and see, what communications they have to have with the operator and other system elements. The next layer in this, or the next rung on the ladder, is what Infineon calls an equipment automation framework. This is the principal communication partner with the equipment, and it acts as sort of a proxy for the higher level systems. And so it'll pass messages on to the factory management system or recipe management or whatever else is providing the sort of MES kind of our control functionality. And then finally, the right rung is the factory automation or equipment automation layer. This is where the factory host systems are, and a lot of the functions that you'll have that do factory level analysis. So you can't really see the details on the right, but I've just shown a segment of that ladder diagram. It goes on for probably 10 or 12 pages, pardon me, as a device may go through the sequence of operations. So let me cover a couple of specifics in here. So and Brian will get into this in more detail when he talks about the reference implementation, but for the carrier handling, there's three types of carriers: the FOUP, which handles the incoming wafers; a multidimensional carrier, which is something that has, let's say, layers of strip charts in there, or strips that you would have chips in. So you can't just reference it with a slot number. You have to maybe give it a complete X, Y, and Z coordinate to know where a device would be or a substrate would be in that carrier. And then finally, nested carriers, where you've got let's say a cart that handles multiple of the multidimensional carriers that you have to track. So this actually complicates some of the E87 sort of messaging and some of the traceability, E142 messaging. So, FOUPs, of course, we're very familiar with the slot IDs, but the multidimensional carriers have a much more complicated location spec, and you have to handle the content maps for all of these pieces. Pardon me. Adding to the complexity, of course, is the number, positions, and sizes of all these things can vary, and so the spec has to be very flexible to support that degree of variability. Okay, process and control job creation and execution. This is very similar to what you would have in a front end. It's a little bit simpler, and so both in terms of the object model for each of those job types and the interactions, but for the messages that are in this integration sequence, they match exactly what the messages would be in a GEM 300 implementation. It's just that there's a strict subset of those that are required for the backend. So even equipment types that don't have a concept of a job need to implement, let's say, a simple job according to these messages, so that the interactions will resemble a more complex equipment and not have to be handled by special cases. Again, that's the beauty of industry standards, is being able to have a common implementation on the sort of host or client side, regardless of the complexity or process type of the equipment. This makes the software engineering task in the factory side a little more predictable than if you had to handle every piece of equipment with custom protocol and custom sequences. Okay, consumable durable handling. Again, Brian will talk a little bit about this in the reference implementation, but this is a new area because it's become more important to know exactly the lot information about chemicals, about fixtures, about fluids, glue, all the different things that go into the manufacturer, because they can all have an impact on the reliability and lifetime of the products. And the manual record keeping is far too error prone to fulfill the traceability requirements for this kind of information now. So again, the distinction between a consumable, these are materials that are used directly in the manufacturing of product that you can directly identify to that. And so glue, mold compounds, wire, etc., these things all have manufacturing batches that you can associate with the characteristics to the actual device. Durables are things that are used during the manufacturing like fixtures or carriers, even in the front end, you keep track of the usage of a FOUP so that you know how long it's been used and what material has been in there and when it needs to be cleaned or refurbished somehow. So in the back end, things like feeders, grippers, adapters, these are examples of durables in the back end. Now, each of these things, both consumables and durables, go through a life cycle of being mounted onto an equipment, being verified. They have to have identification to know you've mounted the right thing for the right parts and recipe. You track the consumption so that you know when you're nearing the end of that batch, and then unmounting. So that life cycle is supported for both consumables and durables in this environment. And the appendices of the TOS, for example, include the list of specific variables, events, and commands that pertain to this. And there is actually a draft ballot underway for consumables in the back end. And so Brian may talk about that a little bit. And those that attend the Advanced Backend Factory Integration Task Force will start to see that ballot being offered up. Okay, E142, here's another one that has been mostly in the domain of wafer mapping. Again, knowing where, which chips are in what position on a wafer. But E142 is covering a much broader set of requirements now as the industry evolves. And so it's not just a matter of substrate device tracking. For equipment types that need to map, let's say, information that pertains to an individual component of the substrate, they need to be able to download an existing map, which gives you the status of information pertaining to that substrate to that point, and then update the content of that map, and then have that re-uploaded to the system for use by subsequent processes. So E142 has taken on a lot of work lately to be able to track all the information that people require in the single device traceability as the device proceeds through its manufacturing life cycle. So in this particular back-end context, the substrate may include wafer strips, trays. It's not just a wafer. And so the detailed information about what happens during that manufacturing step to that substrate is added to the wafer map and then to the substrate map and then re-uploaded for subsequent use. So again, the appendices of the spec determine what's in these, and the industry standards are now being continuously updated to incorporate those elements in the E142 schema. So if you haven't looked at E142 lately, it is evolving to support this higher degree of automation and traceability. Okay, so that's innovation number one. This integration sequence for this whole stuff. And let me introduce Brian Rubo, who is probably one of the most senior people in Symmetrics. It's been working on industry standards for decades and their implementation and support. And he'll be covering the next couple of innovations in this process. So Brian, take it away.
Thanks, Alan. So a second key innovation is how the backend TOS has adapted the GEM and GEM 300 automation standards. And we all know that in the front end of semiconductor manufacturing, they adopted these standards long ago, and it was a major role in their success in automating the factories. And in this backend TOS, it not only requires GEM and GEM 300 and lists which standards to implement, but it shows exactly how to adapt them. The GEM 300 standards were written intentionally to be very generic, so they could be applied to other manufacturing situations. And the backend TOS takes advantage of that and then goes through and explains how to implement these different standards to give you the different features that they want. And there are companies that have both front end and back end manufacturing plants. And there's equipment suppliers that provide equipment to front end and back end factories, both. So by adapting these standards and requiring them and showing you how to implement them, this allows for a significant reuse of software and technology on the factory side and on the equipment side both, and allows for expertise to be shared between these manufacturing groups, which just makes sense. And of course, with these flexible standards, it doesn't mean you always have to implement everything. The standards were intentionally meant to be implemented as needed and as applied. So you don't have to do all of it. You could implement just the subset that really makes sense for particular equipment. One of the real marvels about this adaption of the GEM 300 standards is how all of the standards except the E87 carrier standard is just being adapted as is and follows the standard very strictly. And the only deviations from the standard were in the carrier and tray ID and content verification implementation. So all of the differences between a front end and a back end are handled up front in the back end toss, and then you're able to follow the standards in a very normal and natural way. And the mapping concept is pretty easy. The standards were written using terms carrier and substrate, which are very generic terms. A carrier is really just any container that allows for substrate delivery and or removal. And yes, trays are different physically than like in a FOUP, but by assigning, as Alan talked about, by assigning X and Y locations to trays, we can now treat them in the standards very similar to a FOUP. So now a carrier is being shown how it literally can be a FOUP, a cassette, a tray, magazine, trolley. All these different types of carriers can be used, and the TOS shows you how to apply them. And the term substrate is also generic, and it could mean a wafer, but it also could mean a chip for one equipment or a substrate or a module. I mean, it could mean different things for different equipment. So each equipment implementing these standards simply has to look at, what is the factory delivering to me, what kind of container, and what kind of a substrate am I using, and then the standards can be applied. And what's so important about this is by standardizing how carriers are identified and how the substrates are identified, this means that you can implement traceability, as Alan was talking about. The E142 traceability doesn't really work unless you can uniquely identify the substrates and carriers. And adopting these standards and showing you how to adopt them allows that unique identification to occur. A third key innovation is providing a reference implementation and validation test software. So rather than just saying, here's a specification, please read it, figure it out, that's a very hard thing to do for any specification. But to do better than that, there is also a reference implementation available. So right now we have a back-end simulator that goes through all the different scenarios in the back-end TOS and implements them as defined in the TOS. And that can be used to show people how to implement it. In addition to that, there's a host application simulating the factory host and implements that side of these scenarios. So that is also available, so you can run through all of these different scenarios and see exactly how to implement them to get the right messaging back and forth, to get the right data collection published, and all the other requirements. In addition to that, there is a test available implemented using equipment test with a plugin, and there are some normal standard gem tests in this, and there's also some gem 300 tests available. But the real key is there's plugins specifically implementing the backend TOS requirements, so you can run through a test either against the reference implementation or against a real implementation. It doesn't know the difference. And of course, our Sapiens connectivity platform can also be used to implement the factory host features from the backend TOS. Here's what on the right here, we have the actual back-end equipment simulator shown. This is what the screen looks like. And there's gem communication between that. And on the left, I'm showing you the factory simulator, which simulates the software implementing the factory messages. And the equipment simulation includes all the different features from the backend TOS. It shows you all the material, all of the carriers. It shows you jobs. It has ways to simulate durables, consumables, and other generic gem features. And then there on the factory software are similar features where there's different tabbed windows to go through and run through any of the sequences that you want. And it just requires a manual person driving. The back-end equipment simulator pretty much drives itself once you simulate delivery of the material. But on the factory side, there's some manual interaction, so you can try different scenarios. And what's also nice about the equipment simulation is that it shows 3 different types of ports. Now in the backend TOS, there's 3 different types of situations they're showing and requiring. The first one is for a standard FOUP style carrier, which is following the standards the same way you would for any front end 300 millimeter equipment. And then the port 2 is simulating a delivery of material in a tray. So it's managing the XY locations of the substrates on the tray. And then the third load port is simulating a nested carrier where you have a carrier of carriers. So there's a whole nother dimension physically to that, which is being demonstrated. And here we're showing also specifically the carrier management. As I said, there's these 3 different styles of carriers that are being simulated in the equipment. And in the factory host simulation, just to make it really easy to run these, there's a button to configure the host for the port 1, which is just a standard FOUP style carrier, and a port 2 for the XY tray, and 3 for the nested. So all you do when you're running through the test is decide which scenarios you want to implement, and then in the equipment simulation, you deliver the material to that port. It just makes it really easy to walk through all 3 different types of physical situations that you might run into in the back end as outlined in the TOS. And then there's ways to go through and see all the details going on. So for example, here on the screen, it's going through a tray style carrier and going through. And it walks you through the scenario just step by step. So here in this snapshot, the carrier ID has been verified and it's waiting for the content verification to occur with the host. But it's just very easy to walk through all these different scenarios, which really takes a lot of the pain out of having to learn this, and you can simply run these and see exactly what to do. This also implements job control, so you can select a recipe and select the substrates that you want to process using that recipe. One of the cool things about the way the TOS implements process jobs and control jobs is that it's always using the substrate ID message structure. For those familiar with process jobs and the E40 standard know that there's a couple different ways to identify the material. And in the TOS, one of the key innovations is they decided just to, because of the different types of carriers, they decided to simply always use the list of substrates when defining jobs. And that just makes it really easy to implement, frankly, because it's always being done the same way. And as you run through these reference implementations, it can show you exactly what's happening, what jobs have been defined. It makes it really easy to make your control job and then execute these scenarios. And then finally, we also have the consumable and durable functionality built into the equipment simulation and into the host simulation. And here you can see how it allows you to essentially mount a durable and then simulate the consumable. You can mount the consumable and then simulate consuming some portion of that, and then finally unmounting it, going through the full life cycle of a consumable. And for those interested in the consumable handling and the durable handling in particular, as Alan mentioned, we're moving along quickly developing a new standard, which is taking these concepts and developing them into a full standard that takes these same concepts so that everybody can have very clear uh, and consistent implementations. And we've done the same thing for durables, where you can see exactly how to take a durable and mount the durable and use it and unmount it when you're done. And in particular, this screen here is showing you how there's data related to the durable that can now be collected. So you can identify specific durables and information about them at any time through the GEM interface when this is implemented. And finally, we also have this testing product available, which has built-in GEM functionality and capabilities. And then there's also a very specific plugin which follows the backend TOS very explicitly and breaks it down into specific tests that you can see here on the left. And you can run individual tests or all of the tests or whatever sequence you want. And on the left here, it's actually showing you there's a configuration screen which allows you to configure the tests for a specific equipment implementation. And it's just a really easy way to, as you're implementing the standards, to develop a pass-fail criteria to know when you've implemented it correctly. And then here we're just demonstrating specifically an example of just one piece of these tests, which is running through the consumable requirements from the backend TOS, where it has specific tests for mounting and unmounting and the setup and verification and the consumption of the consumable. So it's just a really easy way to test that when you're implementing this, you're really doing it correctly. And now I will turn the time back to Alan.
Okay, thank you, Brian. That was Brian is too modest. I meant to mention early in this presentation that the software that you've just seen screenshots of was developed mostly by him, along with Jesse Lopez, who is an expert in the equipment test plug-in development part. So, and that software was built under contract with Infineon to help bring this specification to life. So, all right, I'm going to talk about key innovation number 4. Oops, I hit the button too hard, which is procedural rather than technical, and that is transferring this whole integration sequence and the details behind it to the semi-standards community. And I hope this will address one of the questions that has come up regarding whether or not all this we're talking about is proprietary. Well, the TOS itself is a proprietary document from Infineon, but they take a all ships rise with the tide sort of attitude about standardization, and have very generously agreed to share the integration sequence portion of that document with the industry standards community. And so the charter of the Advanced Backend Factory Integration Task Force, which was created, I guess, almost 2 or 3 years ago now at Semicon, near Semicon West, is to explore consensus-based specifications that can enhance the assembly and test capabilities in the back end. And one of our operating principles is to not reinvent the wheel. Let's look at the existing body of mature connectivity standards and leverage what we can in those. And even before that task force was created, that was Infineon's operating principle. And so it directly aligned with one of the goals of the ABFI. And so this transfer has happened. Now, the focus of the task force to date has been a lot of work on E142 because of its importance to the single device traceability. But in parallel, a couple of us are looking at the details of the integration sequence, preparing a subset of the TOS that can actually be reviewed by that entire task force and then balloted and distributed to the industry. So this will take a little bit of time, but it's a great starting point. And as you can see from the software Brian just reviewed, it's very mature and explicit, and ready for further detailed evaluation. So, and of course, Brian is already working on this consumables tracking ballot, which you'll see if you haven't seen it already very soon. So this ABFI it's an energetic mix of participants from major device makers, equipment and software suppliers. So it's the right community to be looking at this information and generalizing it. Okay, so the last poll question is how important is single device traceability for your customers? Again, this is a topic that's been around a while, but it hasn't been vital for except a handful of use cases like automotive and sort of military applications. But question is, for those of you in this domain, how important is this capability? And I think by extension, the standards that support that. So we give people a few seconds to pick an answer there. All right, very important. Well, there we go. That would have been my guess based on what we hear in the industry. So that also tells us that we're on track in terms of supporting the industry's needs with this standardization process. So good to have that confirmed by a good body of participants here. Okay, last couple of slides here. So what is our current status? Well, the target integration sequence is fully defined and included in the latest version of the Infineon's TOS BE. So for those of you that are suppliers to Infineon, you probably have that document already. The software that Brian showed screenshots of is complete, including the host application that exercises that interface between the outside systems and the equipment, and the plugins that validate it against GEM 300 standards and the integration sequence itself. We're in the process of developing training material that matches all these parts and pieces. And this presentation, this webinar, is actually part of the technology transfer process. We began probably last November with a presentation to a couple of SIMI events, and including one of the APC conferences in Europe. But we continue to add momentum to the tech transfer process. So conclusions. I think a lot of us that have been in the standardization business for a while know how long it takes to develop robust production-worthy standards, and it's too tempting to try to engineer something from scratch when, with a little bit of thought and adaptation, proven standards can work. And so that's our philosophy. It's also been very encouraging to see how well the generality that was designed into the GEM 300 standards works in the back end. I mean, Brian mentioned that in the innovation number 2, but with the exception of the carriers, all of this directly applies. And there are a number of companies that have chosen to require GEM 300 components in their back-end requirements, none quite so as explicit as Infineon, but a number of people are moving this direction. So better data collection will support better automation, and that's what we see for the back end. And this is really sort of low-hanging fruit. As people have talked about the need for accelerating back-end automation, the adopting GEM-based technology is the best way to go. All right, so next steps. Of course, this material has been presented to the back-end task force. They're aware of it. We've done major presentations at SemiCon West last December and the APC conference in a virtual conference last year. Today is the first webinar that we've hosted on this topic, but I think it's been a great start, and we're preparing the tech transfer package for the SEMI standards, and of course that'll trigger a process of gathering industry feedback, updating the standards roadmap, and then as commercial companies, people will be looking to incorporate those features into the standard products that we have for connectivity and control. And then finally, promotion, of course, is a continuous activity. Make sure people are aware that these technologies exist. All right, with that, I will thank you again for your attention and participation, and we've got some time for Q&A.
Great. Thank you so much, Alan, and also Brian. Brian's back there for your presentation. And yeah, we're now going to start answering your questions. We've already got some questions coming in. And so just as a reminder, you're just going to look for that questions box in your control panel and type those questions in there. Just know that all of your questions are private, so it's really just the webinar staff that's going to be able to see them. And so we have some time to answer your questions. Let's take a look at the first one, and I believe this question is for Brian. Our company only makes back-end equipment, so we have no familiarity with the GEM 300 standards. How difficult is this going to be for us?
Yeah, thanks. I'll answer that. It's hard to measure difficulty, but if I was a company that had to do that, I would probably assign 2 people to become experts on these standards. Probably 1 lead and then 1 as a backup in case that lead were to ever depart. And if you have a relatively simple equipment, you can learn what you need to know really in just a couple of months. You can become an expert and get your first implementation done of these standards. But having somebody dedicated to learning the standards and being the expert, and then a backup just to make sure that you're covered is really key. because you need somebody who understands the flow of the equipment as you're implementing them. But probably you're looking at a few months of effort to be an expert and be implementing them on a typical equipment.
Great, thank you. All right, and we have another question. This one might be for Alan. I noticed a reference to Sapience on the reference implementation slide. What is that, and what role would it play in a backend factory?
Okay, thank you. Yeah, we sort of glossed over that quickly. Brian mentioned that is a data collection platform, one of our newer products. And it is a candidate for actually implementing the host side APIs all of the features in this integration sequence. It has been used primarily to date as a multi-protocol data collection platform that people could then run, store things into a persistent store somehow, run analytics against it. So it's a very flexible way of dealing with equipment data. And for those that are familiar with the GEM implementations, you may assume that there can only be one GEM interface. Well, the industry standards actually are silent on that. Some implementations require that there is only a single factory host, but our particular implementation of the equipment side allows actually for multiple GEM hosts. And so you could have, let's say, an existing automation system be running parts of the integration sequence while you would have Sapience doing data collection for analytics in the back end. So it gives you degrees of freedom in the data collection and analytics that you might not have architecturally otherwise. So, but it's our production platform for data collection. So thank you, good question.
All right, and then we have another one. How long will the standardization process take?
Brian, you want to take that, or you want me to take that?
How long will the standardization process take? Not sure I understand the question.
Well, let me have a whack at it then. Industry standard developments kind of follow their own calendar depending on the complexity, the urgency of the need, the complexity of the problem being solved, and the let's say breadth and expertise of the participants in the process. Some standards take decades to develop. Some may happen quickly, but then not be general enough to be all that useful. I think in this case, for full standardization of the scope that you saw in this TOS integration sequence, it's probably a 1 or 2 year process to get from start to finish. But the great news is that there is an explicit starting point and a reference implementation. And from my days at Cemitech, when Cemitech and ISMI kind of played that role as the initial system engineers and validation folks, that greatly accelerates what can be a long process. So again, with decades in this area, I'm going to say at least 1 or 2 years. It could also be shorter or longer, but this sort of thing takes time. But that doesn't mean there isn't useful.
Maybe I can use the consumables and durable standard we're developing as an example. As an example, the concepts, I'm not sure how long it took Infineon to develop them, but actually taking those concepts and putting them into a standard, I started that work a couple months ago and put together kind of a first draft of that standard. We've reviewed it as a task force. We'll probably review that a couple more times as a task force. And then I'm hoping for a first ballot for voting to be later this year itself. And the earliest it could be accepted would be in the fall semi-standards meetings later this year. That would be a bit optimistic for it to pass. It's possible, but probably wouldn't pass that quickly, but I could very well see it passing in spring of next year as a very realistic, even if we run into any problems and differences of opinion, that standard would then have been from draft to completion would be about a year. And that's pretty fast for a standard to be developed, frankly.
Yeah, true. Yeah, and just because it's not fully standardized from start to finish doesn't mean that customers and suppliers of these interfaces can't get lots of benefit along the way. Because it, again,
Yeah,
as Brian said, it is leveraging existing GEM 300 standards, and so that investment would not be wasted or supplanted by something else. It's every step along the path is a useful step. So, great question.
Thank you both. And I think we have time for one more question. And so we're hoping that you can address this one. Traceability breaks with tape and reel. How is PDF addressing this?
What do you mean breaks?
Let's see
Is
if we
it
can
breaks?
get.
Yeah, I don't think we would agree that it really breaks the standards or the adaptation of the standards. It's just one thing to deal with, and PDF itself is very invested in working with the standards community, and working with the tape and reel feeders is one of the things that we are addressing in the backend task force, is making sure that tape and reel and all the other delivery mechanisms can be handled. So it's definitely a topic that we are involved in the task force. So when the task force finishes the work that we're doing, we'll have a clear strategy on dealing with that and the many other things that are dealt with in the back end.
Yeah, and that's the other thing that may happen there, is that the requirements for traceability may push the tape and reel actual suppliers to another level themselves. I mean, you already have, of course, IDs for what reel you've got, but knowing the traceability of the individual components on those tape and reel devices would that may be a downstream requirement or an upstream requirement that gets created as a result of this. So.
Yeah, and certainly reporting on tape and reel information for, full traceability means you have to be able to know which tape and reel it came from, and which item from that tape and reel, exactly where it's being placed, or if it's discarded and what's happening. That's what traceability means when you're fully implementing it. So that's very much a use case that's in our discussions.
Yep, great question. Okay.
All right. Great. Thank you both so much. I think we're going to go ahead and wrap this up. And so again, we want to thank both of our presenters, Alan and Brian, for your information. And we want to remind everyone that you will receive a follow-up email within 24 to 48 hours that will have a link to this recording. And so on behalf of the Symmetrics Connectivity Group and our presenters, thank you all for joining us, and we hope you enjoy the rest of your day.
Thank you.
Thank you, everyone.
Okay. And we want to give a shout out to Kim Deitch, our marketing director, who of course facilitated the creation of all this. So an unsung hero in this whole domain. So thank you, Kim.